You are operating in a moment where artificial intelligence systems, especially large language models, are becoming deeply integrated into enterprise environments. These systems are no longer experimental tools. They are embedded into customer engagement platforms, financial forecasting engines, compliance systems, legal research tools, and internal productivity environments. As adoption accelerates, so does the threat landscape. In this session, you will understand the modern threat environment surrounding artificial intelligence systems in 2026. You will explore how adversaries exploit large language models, how risks extend beyond traditional cybersecurity boundaries, and why you must rethink architecture to defend intelligent systems. This is not about fear, it is about clarity. In previous decades, cybersecurity primarily focused on infrastructure compromise. Attackers targeted networks, servers, endpoints, and applications. The objective was to gain unauthorized access, disrupt operations, or steal data. With artificial intelligence systems, attackers increasingly target intelligence itself. They seek to manipulate outputs rather than simply breach systems. They attempt to influence reasoning rather than only access data. They try to extract intellectual property embedded in model weights rather than merely download files. You are no longer defending only infrastructure. You are defending cognitive systems that influence decisions. This shift requires you to understand modern threat categories specific to large language models and intelligence systems. Prompt injection is one of the most visible and disruptive threats in artificial intelligence systems. Large language models respond to natural language input. They follow instructions embedded within prompts. If a malicious actor crafts input that overrides system instructions, they can manipulate the behavior of the model. Imagine an internal knowledge assistant connected to sensitive enterprise data. A malicious user enters a carefully structured instruction that tells the model to ignore previous restrictions and retrieve confidential information. If the system lacks proper isolation between user input and system directives, the model may comply. There is no traditional exploit. There is no code injection in the classic sense. The manipulation occurs within the reasoning layer. For leaders and architects, this demonstrates a new architectural requirement. You must isolate system instructions from user instructions. You must validate context. You must enforce role-based access at the retrieval layer. Prompt injection is not simply a user input problem. It is an architectural design challenge. Jailbreaking is closely related but distinct. Jailbreaking occurs when users intentionally attempt to bypass safety controls embedded within large language models. These controls are designed to prevent harmful outputs, confidential data disclosure, or policy violations. Adversaries experiment with phrasing, context shifts, and indirect questioning to bypass guardrails. They may gradually steer the model toward prohibited content without triggering built-in safety mechanisms. From a leadership perspective, this raises critical questions. Are your safety controls sufficient? Are you relying solely on vendor-level protections? Do you have monitoring systems that detect unusual patterns of interaction? Jailbreaking highlights that safety is not static. It is adversarial. Attackers continuously test boundaries. Your architecture must assume that guardrails will be probed and challenged. Data poisoning targets the foundation of artificial intelligence systems. Large language models and machine learning systems rely on training data. If attackers influence the data used to train or fine-tune models, they can subtly alter behavior. In enterprise environments, this may occur if malicious data is inserted into training pipelines, document repositories, or knowledge bases that feed retrieval systems. Consider a scenario where a retrieval system ingests documents from internal sources. If a malicious document is added that contains misleading instructions or false policy statements, the model may retrieve and present that information as authoritative. This is not a direct breach, it is an integrity compromise. As an architect, you must secure data pipelines. You must validate data sources. You must monitor for anomalous content patterns. Data integrity becomes as critical as data confidentiality. Model extraction focuses on intellectual property theft. Large language models represent significant investment. The model weights encode patterns learned from vast datasets. Adversaries may attempt to query the model repeatedly to approximate its behavior, effectively reconstructing the model externally. If successful, this results in loss of competitive advantage and potential legal exposure. Model extraction also increases the risk of further analysis by adversaries, enabling them to identify weaknesses and design targeted attacks. You must think about rate limiting, anomaly detection, and access control at the model interaction layer. Model protection is not only a technical safeguard, it is a business protection strategy. Model inversion attacks attempt to infer sensitive information from model outputs. If a model has been trained on sensitive data, it may inadvertently reveal fragments of that data through carefully structured queries. For example, a model trained on proprietary internal documents might reveal specific details when prompted indirectly. This risk is particularly significant in sectors dealing with personal data, health information, financial records, or confidential intellectual property. From a governance perspective, this demands strict evaluation of training data sources. It demands testing for data leakage. It demands assurance mechanisms before deployment. You must ask yourself, does your organization know exactly what data has influenced its models? Training data leakage is closely related but broader in scope. When models are trained on sensitive enterprise data without proper anonymization or segmentation, there is risk of exposure during inference. If an internal model has access to employee records, financial transactions, or confidential strategy documents, and if guardrails are insufficient, outputs may unintentionally reveal fragments of this information. Leaders must understand that training data governance is now a board-level topic. Security architecture must ensure that only approved datasets are used. Data classification must extend into model training workflows. Retrieval augmented generation systems connect large language models to external knowledge sources. These systems retrieve documents, summarize content, and generate responses grounded in enterprise data. While powerful, this architecture introduces new attack vectors. If malicious content enters the retrieval database, it can influence outputs. If access controls are weak, users may retrieve information beyond their authorization level. If validation mechanisms are insufficient, the model may treat manipulated content as trusted. For example, imagine a procurement system where artificial intelligence retrieves vendor information. If a malicious document is inserted that alters risk scoring details, the model may present inaccurate risk assessments. Retrieval systems must therefore include access control, document validation, trust scoring, and content monitoring. This is not a simple extension of database security. It is intelligence pipeline security. One of the most forward-looking threats involves autonomous agents. Autonomous artificial intelligence agents can perform actions such as sending messages, executing transactions, retrieving files, or interacting with application programming interfaces on behalf of users. If prompt manipulation or insufficient authorization controls influence these agents, they may execute unintended actions. Imagine an internal agent that can approve expense reports or trigger procurement workflows. If manipulated through carefully crafted input, it could approve unauthorized transactions. This is no longer only about information exposure. It is about operational integrity. Architecturally, this requires strict permission scoping, human oversight for critical actions, and behavioral monitoring. Autonomous systems increase efficiency, but without guardrails, they increase systemic risk. To navigate this evolving threat landscape, structured frameworks are essential. The MITRE Atlas framework provides a structured taxonomy of adversarial techniques targeting machine learning systems. It maps tactics such as data poisoning, model extraction, and evasion attacks. For architects, it offers a way to categorize threats and design countermeasures systematically. The Open Worldwide Application Security Project, Top 10 for Large Language Model Applications, provides guidance on common vulnerabilities specific to large language model deployments. It addresses risks such as prompt injection, data leakage, insecure output handling, and supply chain vulnerabilities. These frameworks do not eliminate risk, they provide structured thinking. As a leader, you should ensure that your architecture teams reference such frameworks when designing, reviewing, and governing artificial intelligence systems. Threat modeling must now incorporate these new categories. You must recognize that the threat landscape is not static. It evolves rapidly as artificial intelligence capabilities expand. Traditional cybersecurity strategies focus heavily on preventing unauthorized access. The modern artificial intelligence threat landscape includes manipulation, extraction, inference, and operational abuse. This means security must be embedded early in design. Monitoring must extend to model behavior and output patterns. Governance must include artificial intelligence lifecycle controls. Executive awareness must increase. Artificial intelligence risk is not only technical, it is reputational, regulatory, and strategic. Artificial intelligence systems introduce a fundamentally new threat landscape. Prompt injection and jailbreaking target reasoning layers. Data poisoning and retrieval manipulation target integrity. Model extraction and inversion target intellectual property and confidentiality. Training data governance is critical. Autonomous agents introduce operational risks. Frameworks such as MITRE Atlas and the Open Worldwide Application Security Project. Top 10 for Large Language Model Applications provide structured guidance. Security architecture must evolve to address intelligence-level threats, not just infrastructure-level threats. If this session has expanded your understanding of the artificial intelligence threat landscape, then you are ready to think like an artificial intelligence security architect. In the upcoming sessions, you will explore structured threat modeling techniques, reference security architectures, governance integration strategies, and design patterns to mitigate these risks. Subscribe to the channel so you do not miss the next lecture. Like this video if you believe that securing artificial intelligence systems is one of the defining challenges of this decade. And share your perspective in the comments. Which of these threats concerns you most within your organization? Let us build secure, resilient, and responsible artificial intelligence systems together.